So Ampere's law, in the case of the analysis we just did, tells us that the magnetic field multiplied by the length of the coil is equal to 4 pi k prime times the current enclosed by the integration path. It follows immediately then that the magnetic field is equal to the 4 pi k prime times our total enclosed current, the current times the number of times it penetrates the loop, divided by the length, and that the magnetic flux of the phi b magnetic flux for a single loop is magnetic field times the area of the loop. And since I've used capital A for, well, I'm going to just risk that we get confused there. I sometimes use capital A for amps. Usually I write it out so as not to confuse it with area. We multiply the magnetic field times the area. The magnetic field, in this case, being perpendicular to the area. We get the full magnetic field times the area, and that's a flux through one loop of our coil. There are 300 loops. We're just doing the magnetic flux for one loop, and very simple to see that we multiply the magnetic field by the area, and we get that magnetic field, multiply that by the number of coils, because each loop, by the number of loops in the coil. This is the flux for one loop. This will be the flux for all the loops. We multiply this expression by n, which is the number of loops. And of course we get an n squared here. And there's our total flux. The EMF induced in this coil is going to be then the derivative of the flux. And the only thing that can vary is the current. So that if we do the time derivative of this magnetic flux, we can factor out everything except the current, and then we take the derivative of that, and the derivative of the current is di dt, where I've replaced the capital I now with the lowercase I, indicating that we have a time varying current. The original problem, we had a constant current, 12 amp constant current. Making the transition to a variable current, we just replace capital I with little I, and in calculating then the rate of change of the flux, we end up with this expression, multiple of di dt. This rest of this is all just dependent on the number of loops, the area of a loop, and the length of the coil. So we also want to say that the EMF is equal to the negative of the inductance times the derivative of the rate of change of the current, the time derivative or rate of change of the current. So that this inductance, which we call L, is going to be our negative 4 pi k prime a n squared over the length. So we have an expression now for the inductance of the coil. Now this is an approximate expression because remember we assumed that the magnetic field, which we calculated only for the x-axis, actually applies everywhere else within the coil. Okay, so calculating the inductance of the coil, we plug in our 3 square centimeter cross-sectional area, our 10 centimeter length, and our 300 loops within the coil, and we do the arithmetic, and you can correct me if I'm wrong, but I believe we end up with 3 times 10 to the negative 5th Tesla meter squared per amp. Now I've converted the 3 centimeters squared to meters squared, and the 10 centimeters to meters. And we see then that we're going to have a meter here in the unit, and we're going to have a square meter here divided by a meter here. That's going to give us Tesla meter squared per amp because the only units here are the units of the area and the length. Now, Tesla meter squared per amp, the unit of inductance, where the magnetic field is in SI units, the length in SI units, and current in SI units, is going to be the SI unit, the Henry. A Henry is a Tesla meter squared per amp, and we get this for the inductance of the coil.